Buongiorno. Good morning, everybody. Again, good morning. Parte richiusa la porta del bagno perché sennò So first of all, the code for today is 224040. The code, the token that you have to use for confirming your seat here. Okay? Is it clear? Well, then sharing the screen. So last time we stopped here talking about, say, software development. And software development is based on the implementation of so-called algorithm. Algorithm is a word that the origin of the word algorithm is disputed or almost unknown. Someone says that comes from the name of a mathematician, Arab mathematician called Al-Khwarizmi, or some other says that derives from the Greek algorithmos. Anyway, algorithm is, let's say, defined as a succession of instruction that define the operation that have to be performed on input data in order to produce a result that is called output. Of course, the input and output data can have different forms, and also thanks to say innovative algorithmic techniques such as the one of artificial intelligence, because you have to remember that also the properties and the capabilities of artificial intelligence are based on even more evolved algorithms. And the importance is that now we have the capability to process data that are in the different forms that we have already seen. So that might be numbers, might be text, might be, let's say, structured and unstructured text, like the one, for example, last Thursday, we have seen a video. You have seen a video with a, let's say, real-time translation in English. Of course, the quality of the translation was not so good, but anyway, was in a shape that made the speech in Italian understandable also for English readers. Of course, this translation and the video that you can find on YouTube, and now you can find billions of different videos. Of course, you can imagine that they are not translated. So the translation is done upon request by using a translation software, and in particular for that case, it was by using a software that translates in other languages the natural language, speech. And the translation of natural language, text or speech, is extremely difficult, because, and the speech is even more difficult than text, because if you hear yourself talking after having recorded, you understand that the way we are talking is not linear. We are not reading a book while we are talking. Okay, so it's extremely unstructured, and it's really difficult to reconstruct the right meaning of sentences. Okay, and this is done through artificial intelligence algorithms, machine learning, that are capable to process the natural language. So in this case, the input here is the speech, the sound, and the output is the text that you read. So inputs can be of really different forms, as well as the output according to the need of the user. So using more, let's say, analytical terms, an algorithm is a transformation F that, applied to data X, produce results Y. An algorithm has given characteristics. The first characteristic is the generalities. That means that an algorithm should be able to solve all the problems of the same class. Using a trivial example, an algorithm that makes the sum of two numbers have to be able to compute the sum for every number, not only 3 and 5. Okay, the algorithm that makes the translation from the Italian speech to English should be capable to do this kind of translation, even though the speech comes from a man or a woman, and so on. It should be capable to recognize the voice of both, and so on. This is a wrong translation, so let me correct. In interest. Left. Okay. Better this way. Of course, the algorithm should be finite, should be capable to give a result after a certain but finite number of interactions, of let's say cycles. Okay, otherwise it is not let's say an efficient algorithm. Actually, it's not executable. Okay, should be unambiguous, because the algorithm, the design of the algorithm should drive also the programmer in writing the instruction of the programming code, and of course this instruction must be written in a way that is impossible to misinterpret it. Okay, and of course it must be executable on the machines that we have available, on the computer that will host the algorithm for running it. There are different types of instructions. A question. Sorry, Professor. The second feature. The algorithm must end at a certain point of time. Okay, should produce a result after 1 second or after 20 years, but it must come at an end. Of course, the duration of the execution of the algorithm depends on how much complex it is. Do you remember the slide that we projected at the beginning? Yes, it's also in the book, but anyway. Do you remember at the beginning the first slide that I projected, one of the first slides that I projected, talking about the coding of DNA? The algorithm for the coding of DNA, of course, became more and more efficient, but also 20 years ago was almost impossible to decode the DNA in a short time. Now the computing capabilities is increasing really dramatically, and we are capable to compute the DNA, to calculate the DNA structure in a few hours. But always, in both cases, the algorithm that does that is a finite algorithm. There are problems, also mathematical problems, that are not computable according to the current knowledge, and they are not solvable with finite algorithms by now. Okay, but also a mistake can make an algorithm not finite. Okay. We will come back on this later on when we will talk about quantum computing. These are some categories of instructions: start, end, transmission, allocation, calculation, comparison, I gave the access to hundreds of persons. I don't know if I miss you, but I don't think so because I checked all the message. Try again, and maybe I didn't get it. Use your Uniroma address, studenti.uniroma1.it. Otherwise, the risk, okay. I will check again today, but I gave, yeah, in the weekend I gave the access to I think about 50%. Comparison and conditional jump, conditional jump. So there are techniques for defining data and declaring, for example, the assignment of a value to a variable that we can call A, and where we can assign the value to such variable. Of course, I will not go in depth in this because this is another course, or better, another degree of computer science. But if you are interested in this kind of topics, you can attend, for example, and have as a, let's say, voluntary exam the course of business intelligence that is given by Professor Velardi. Is a course of the Faculty of Economics that is given by a professor of computer science, and it's useful to complement also the content of this course. Okay, if you want to go in depth. Okay. There are several ways to represent the algorithm, also in a graphical manner, using block diagrams and flowcharts. Of course, for doing this, there is a symbolism. Okay, so this is a way for using block diagrams. So the rectangular box is the instruction. This kind of box is the beginning and the end of an algorithm. This box is the read and write instruction, and this one is the choice, the conditional. So where you have one input and two exits, yes or no, black or white, 0 and 1, basically. Okay. And this is a flow chart. There are several programming techniques. A technique is a way for represent a way for dealing with problems. Okay, there are problems that are structured and can be solved by using, let's say, an Aristotelic approach, decomposing the problem in several sub-problems. And this is the so-called top-down approach. I mean, an example, this is should be the typical approach that you can have when you write a thesis. You have a problem. You write down a table of contents where the problem is decomposed in a number of sub-problems. And again, the sub-problems are decomposed in other sub-problems and so on. This is a top-down approach. Think about a tree that has, and this should be, let's say, the golden rule for facing and solving a problem through programming and in general. But this is not always possible because we don't have the full knowledge of the problem. So we start to solve problem from the bottom, identifying small problems that are visible, and then we put together all the pieces, trying to say uniforming and doing the unitary vision or unitary approach. This is example what we are doing for the Irina for the project. You know that we have a piece of platform from one side, another piece from the other side, and at the end of the game we will try to put all the bits and bytes together in a unique platform. This is a bottom-up approach indeed. Okay. Many programming languages allow the so-called structured programming that considers these two approach and allow to have pieces of programs that can work independently or can belong to an overall complex structure. So they exist themselves and they are self-sufficient or can be inserted in an overall structured approach. Unfortunately, I don't have the translation in English of this, but I will do it for you. And this is a joke that is quite old joke that circulates in, let's say, consultancy companies. We have seen last time that there is a phase where the user requirements are collected here from the customer, from the client. So what the customer desire, basically, what was understood by the project manager, how was projected by the analyst, what was programmed by the programmer, what was, let's say, sold by the consultant, the documentation of the project, the installation of the software, the billing, the continuous implementation of the software, and what would have been really the need of the customer. Okay, And these are all the mistakes that are made usually in a software development process. Types of languages. Machine-oriented languages. There are still languages that are oriented to the machine. And so the programming is done by using all the binary codes or a really simple and but efficient programming technique language that is oriented to the machine, and it's very difficult to learn, and implies the knowledge of the hardware architecture of the computer. But big supercomputers are still programmed in such kind of languages. Then there are the, let's say, user-oriented languages that are different types. Imperative languages, such as the BASIC, for example, or the Fortran, or the C, okay? Where, a step back, why programming languages are called actually languages? Because as every language, they have a syntax. They have rules to be respected in order to teach the machine to perform an algorithm. So all the languages have strict rules that you need to know. These languages can be imperative, so it's like basic do, while, no, if, so can be object-oriented languages. That means that you don't, more or less, write lines of code with using the language, but you work on visual objects to which the programmer assigns certain actions or characteristics. Of course, this is a way for making things easier for the programmer, but behind the codes, the objects, sorry, there is still an imperative language that is written automatically. For example, let me open a page, a web page. I open my one. Just to let you understand what is the meaning of object-oriented programming. You see here, I need to enter, otherwise. Doesn't work. Okay. It didn't let me enter. Again. Let's try again. Okay, I mean, you see here, now here I can modify the web page, okay? And I can enter here my website, and you see here, I have a number of objects that are headings that are pages that I can manage through a visual interface. And this is extremely easy. You just have to learn a bit how to create an hyperlink, how to make it bold, and I can write directly into. But behind this, there is always a code. Okay? There is always a code that is produced when I do a certain action. I don't remember which is the button. You see here are the pages. Just the HTML. I don't remember the way to visualize the HTML, but behind this there is the HTML code that is produced real time when I do a certain action. The way to visualize change from browser to browser. That should be somewhere I can see it. Control U. Yes, right. So this is the code that is produced behind the page that we have visualized. And if you are, let's say, good enough as a programmer, you can modify directly the code inside here. Okay. Oh, visualizza sorgente. It was okay. This one. Okay. So let's go back to a normal page, and that's it. Then there are functional languages, such as, for example, functional language that we can have here is yes, is MATLAB. MATLAB is a programming environment. It's not installed, where you have predefined, or you can define yourself, functions that treat inputs in order to obtain certain outputs. You can have R, for example, is another functional language. You have here logic base of declarative language that are used for example, machine learning and the implementation of artificial intelligence algorithms. Okay. Then you have two different typologies of programming language with respect to the way how they translate the code, the language, into binary code. That is the one understandable by the computer. This can be interpreters or compilers. For example, the HTML is an interpreter. So every time we make an instruction, this is immediately interpreted and translated into, say, binary code. With the compilers, we have to pass through a process that produces an executable file, the one that is distinguished by the .exe characteristics, that is in, let's say, binary code. So you cannot read this executable file. You have to decompile it. Okay, and this is the way how all the program, like office automation programs and many other routines are working. So you launch the executable file, the exe, because that is compiled. While, for example, if you use an HTML or use R or MATLAB routine, these are interpreted, and you can read what is in the file. Okay. These are some of the languages. And now we have to talk a bit about the next generation of computing. That is quantum computing. That is, let's say, an extremely complex approach to computing. Think about that. The current approach to computing is based on the knowledge about the way of working of electronic circuits that comes from the Second World War. The improvement in the computational capability was mainly due to miniaturization technology rather than knowledge about the way the transistor work. The computation has been improved, capability has been improved because we were mainly able to integrate more and more transistors within a silicium plate. Okay, now this technology is completely different and disruptive. Okay, is let's say a really huge technological step, because these computers that are still under development are based on knowledge that comes from, let's say, the deep physics, the quantum physics, where the way of working of these computers is based on the way of working of atoms. So the qubit, the so-called qubit that will replace the bit that we know, that has only two positions, 0 and 1, has a so-called superposition, where there are infinite positions between 0 and 1 that can be used. Of course, I'm in a quantum box, maybe. So, through this kind of computing, can be defined the infinite state of the phenomenon that we are computing. And we are capable to representing all the states simultaneously. So this is the classical physics, no? Predictable outcomes, variable are continuous, finite known values, and so finite algorithm, no? Always with a known state. Binary numbers are in the form that switch from on to off and vice versa. Here, all these classical rules of physics are changed. So we can represent infinite states between 0 and 1. Many positions can be represented simultaneously, no? And the state is undetermined until it's measured. And this is what we call the superposition. The superposition is represented by the so-called qubit that are carried out by atoms, ions, photons, electrons, no? And now the control devices, what we have seen, central processing units and memory and so on, are built for working with atoms, ions, photons, and electrons. The other characteristics of the qubit is the so-called entanglement, no? That allow multiple numbers to be represented simultaneously in the same position. This means, at the end of the game, that, for example, computers will not have any more the problem of heat dispersion or heat production that they have now, that, let's say, hinder somehow or limit the capability of computing. and this is a mainly physical issue, but computers will be able to compute in an exponential scale a huge number of instructions in the same unit of time that is not comparable with the current capability. I mean, billions of times more efficient than the current capabilities of computing. And this is see here the position, the classical bit and the superposition where. So have you seen the algorithm and the processing of an instruction is sequential in normal, say, current computing machines. You have seen the machine cycle last time, okay? That is done step by step. Now, in some years, quantum computing will be able to perform millions of computation in parallel at once using the superposition. Okay? And of course, there is also an ongoing strategical battle among big players to arrive to have the most advanced quantum computer. But this is a huge problem also, because these computers will be able to solve problems based on root computation that are not solvable with the current computers. What does this mean? You know, for example, I don't know if you know, but I'll tell you, that security algorithms, encryption algorithms, are based basically on the usage of prime numbers. According to the, let's say, Riemann, the mathematician, theory, that was not so, the Riemann conjecture, that is still not solved. If you multiply two prime numbers big enough, you obtain a number as a result from which you cannot go back to the number that originated. And this is the basic principle upon which all the cryptography techniques and security techniques are based. In order to go back to the original number, you need a computation that would take hundreds of years. Making this computation almost not finite. So you cannot break password security system based on this technology, on 120-bit encryption that is done by multiplying 120-bit numbers, prime numbers, with the current algorithmic techniques, even you know the passwords or the codes of doing that. With quantum computing, this is something that is possible in seconds. Some years ago, an Italian mathematician working in the United States announced, for joke, and he said that he solved the Riemann conjecture. Knowing that on this conjecture was based the cyber security all over the world, after half an hour, he had the FBI in his office. And he had to say, "No, I was just joking." Okay. Okay. I will. Which are the characteristics of quantum computing? Will be easy to make and operate. Small in size, because of course we will be dealing with atoms, no? So atomic structures. We won't have any more what we know, and the computation will be performed in microseconds. Of course, there is still a lot of research needed for making of this quantum computing, let's say, a commercial state of the art. You can Google it and you can find a lot of startups, but also over the top, that are working on quantum computing, and this is exactly what I just said as an example for the cryptography, that quantum computing may become really can jeopardize the current cyber security systems. For this reason, no? Because for factoring a big number, factoring the big number in two prime numbers, it could take trillions of years of computation, while a quantum computer could do it in 2 minutes. Okay. So we completed this part. And now we talk a bit of transmission networks, data transmission. Okay, we discovered during the pandemic let's say the full use of networks. There are several means of transmission, physical, I mean, that are, let's say, the tangible ones, cables, copper. Let me correct this. Copper twisted. Okay. Twisted. That is the usual cable that we have in all our houses, the telephone cable, basically. We have coaxial cables for transmitting data. We have fiber optics, that is the, let's say, state-of-the-art means of transmission for digital transmission. Then we have the wireless. These are the wired. Then we have the wireless transmission media, such as radio waves, so the radio spectrum. Imagine also the radio spectrum, but also like the wired transmission means, like a water tube. And in the case of water, the capability to transport the water depends from the height, from the diameter of the tube. Here, the capability depends from the physical characteristics of the mean of transmission. The copper twisted pair has, let's say, a relatively low capability to transmit one big quantity of data. It was possible to deploy the copper twisted pair for a long time after the usage in telephone networks because of the capability of, thanks to algorithmic techniques, to compress the data that were traveling on, thanks, I'm talking about ADSL, for example. ADSL is a transmission technology in all its evolutions, V, ADSL, X, ADSL, and so on, capable to, let's say, squeeze data and transmit this data over the copper twisted cable. This was, let's say, good on one hand, because we were able to fully deploy the existing phone telephone infrastructure, also for having, let's say, the internet at all. But on the other end was, let's say, and this is something that when we talk about, do you remember the Boston Consulting Group Matrix? the cash cow, the stars. Remember this? Let me find it over the internet. Here we go. In English better. This is quite famous in management. If it opens. Come on. Let's try again. No. Broken. Okay. So this is, as I said, this is quite famous. So on this axis, you have the relative position on the market. On this axis, you have the business growth rate of the market. And here you have the positioning of your product. Okay. When you have a, let's say, a new technology, even if this technology is disruptive, like could have been disruptive, for example, the fiber optics 20 years ago. Okay. 20 years ago, fiber optics was already existed, more than 20 years ago, 25, for transmitting data. But the technology was not, let's say, it was too much ahead for the state of the market at in that period. Okay, even though it was already mature for being deployed. Telecom operators still have available that time the copper network that would have been fully usable by using ADSL technology. So why, at that point of time, they should have replaced the copper with the fiber optics, investing a lot of money? The answer is here, because at that point of time, the copper network was a so-called cash cow. All the players, the incumbent telecom operators, have a high position on the market. They were really few. The market was not so liberalized in Europe and all over the world. The investment needed for providing a service was relatively low, because the network was still there. They just had to use the ADSL. So they didn't make any other investment, and they used the copper network as a cash cow for producing money, providing the minimal level of services to anyone by using ADSL, and they get revenues for another 10, 15 years without investing a lot of money. Of course, now the copper network is not capable anymore, sufficient anymore to support the high quality, the enriched media, for example, that we use, the high definition television, and also with the help of states, government, that put a lot of money, the technology moved from the copper network to the fiber optics network in order to guarantee the bandwidth needed for supporting, let's say, added value services and, let's say, added value and over-connected. For example, without fiber optics, all the call that we had in the lockdown would have not been possible. Without broadband dorsals in fiber optics, we experienced also some problems in connections when everybody was using a video connection because the network was not prepared to host all together. The technology behind was not sufficient for hosting all this kind of communication. And then for moving, so now the fiber optic, the copper is entered in this phase of this mission. And there is a need of higher investments for bringing the new generation of services. But again, do not forget that the technology of fiber optics is not new. The 5G that needs some more investment, the 5G and fiber optics are complementary. They cannot exist the one without the other, because the cell of 5G are connected through fiber optics. These two technologies are not innovative, but they came at the moment where the market is ready for accepting them. There are still the 4G network that are working, and let's say in a quite satisfactory manner. So there is not interest from the operators to replace in total rapidly the 5G because the 4G, because the 4G is still a cash cow. So the lesson here is that even you have the best technology ever, you have to think about the right timing for introducing it on the market. Because you have several effects, such as the network effect, for example, that may hinder the deployment and let's say the profitability of the usage of this technology, just because it's not the right time to enter in the market with the technology. So here, all the players waited for replacing the copper with the fiber optics. The players are waiting for replacing the 5G, the 4G with the 5G. Of course, 5G now has been implemented in big cities where there is a demand that justifies the investment. But otherwise, still it's cash cow. The other places, they will see you have the 4G. It's clear? Wireless transmission. Also here, as I told you, we are observing also in this day a reshape of the way how the radio spectrum for data transmission is used for television, for low frequency transmission is used, for example, for the IoT devices. Now, every analogic transmission on the radio spectrum is going to be abandoned in order to leave space to the digital transmission that is more efficient. It uses lower bandwidth. With one channel of analogic transmission, you can have at least 10 channels of digital transmission. Okay, so in the next years, also the frequency modulation, FM, that we use for listening the radio will be abandoned in favor of the digital transmission of radio programs. This is really the last one. Then everything will be digital. Okay. Have you ever think about how a switched telephone network works? The old-fashioned telephone network that is still in place, you know? Even though now the management of the telephone network is digital, it's still based on what we call the local loop. If you go along the streets, in the surroundings of your home, probably you have noticed that there are boxes where sometimes you can see people working on cables. Did you notice that? There are small gray and orange boxes that are close to the buildings. These boxes are the so-called local loop, where all the cable copper connection arrive from any house that is in the surrounding. Of course, now you can choose the operator that you want to use, but anyway, a cable starts from your house and arrives in that box. This is the local loop through which you are connected to a switching center. The switching center is connected to another one, and so on, because it is not feasible that you are connected to the all potential user in the world. No? So every user is connected to a switching center, the box, and switching center are connected among them. Switching center now are digital, and the connection is very fast between them. And in this way, all the circuits are closed until the call arrives to the receiver, to the final receiver. The connection between switching center is made through a trunk that can be in different cable and wireless means. So you have here your local loop, you have the switching center, and you have the other local loops. So I'm here, Irina is here. I call Irina, I'm connecting to my local loop. The local loop is going to connect to the switching center that decide where Irina is, knows where Irina is, and connects to the local loop where Irina house is connected, and connects to Irina, and to any other, of course. Okay? This is the typical way of working of the circuit switching. This is what exactly, if you have seen the movies of 1 century ago, of the 30th of last, where there was usually a woman in the switching center. So you were using the telephone. Please pass me the 5678 of New York. And the woman with the switching board were making the connections. Okay? This is circuit switching. This is exactly what now is done through switching centers, automatic switching centers. This was done by hand, by persons, switching the local loop with the city or within another state and so on. The big innovation that we observed in the last 50 years was the transition, even really gradual transition, from circuit switching to packet switching. That is the principle at the base of the functioning of the internet. Okay, let's see after what does it mean exactly. Of course, you need a device for connecting to packet switching networks, such as a network card or a modem. These are the technologies, for example, the ADSL that were used. And you have the different kind of networks: personal area network, local area networks, and metropolitan area networks, wide area networks. Local area networks are based on, let's say, several topologies. The most used topology that you can also observe by just exiting the room here is the star topology, where you have the hub, local loop, that is like a local loop with a lot of connections. And this is the star topology. But you can still find the ring topology or the bus topology that are, let's say, more inefficient with respect to the standard that is now the star topology, where you have a hub and all the devices connected to this hub that works like a local loop and transmit data according to the routing protocol. For example, if you are connected to the Wi-Fi of Sapienza, you are using basically a metropolitan area network, because Sapienza is sparse more or less all over the city here, and with the same credential, you connect here, you connect to the Faculty of Engineering, you connect wherever you go in Sapienza buildings. Okay, because we have a metropolitan area network. Of course, this metropolitan area network is connected to the widest internet that is, let's say, a geographical. No? And here you have the way how local networks, the network that we have here, are connected to, this is another one, this is another one, your device is a host, and through a router gateway are connected to biggest subnet that themselves are connected to wider area network. Okay, I've stopped here for today because the last slides are more on the internet and I will go more in depth with that. Any question? Any question? Ok. Allora, prima di uscire. How long do you think it will take to migrate all to digital? Well, basically, it's done. So we are migrating everything to digital. Just the radio, the analogic radio resists in transmission because of, let's say, legacy systems, and they still think about, let's say, less developed countries in Africa, Asia, some in Asia, and still there. If you switch off the analogic radio, I don't mean only the, let's say, the commercial radios, okay, but also the service radio channels, analogic radio channels.